Right. Well, thank you, Myra, for the introduction. So I'm very and truly pleased to introduce Karthik Duraisamy. Is an associate professor and, of course, a faculty member of the Aerospace Engineering Department and director of the Center for Data-Driven Computational Physics at the University of Michigan, Ann Arbor. Karthik holds a PhD in Aerospace Engineering and a Master's in Applied Mathematics from the University of Maryland. And his research interests are tremendously relevant to this data-driven seminar series because they revolve around computational modeling, including data-driven and reduced order modeling, statistical inference, numerical methods, and also physics-based modeling. Karthik is also a founder and chief scientist of the Silicon Valley-based startup, Geminus, I believe, .ai, which is focused on developing digital twins for industrial processes. So without further ado, I would like to give the floor to Karthik, who's going to give a talk on data-driven reduced order models for multiscale and multiphysics systems.
Right. Thank you for the introduction, Luca. So let me go to full screen here. And yeah, I think we're all good. All right, thank you for the introduction. And as I was saying, I was expected to be in the UK at this time, but I'm also very happy to give this talk. And I think this also reaches a broader audience this way. Before I get started, I want to quickly give acknowledgements where acknowledgements are due. So a lot of this work was done in collaboration. In fact, these guys did most of the work. So Cheng Huang was a research scientist in my group. So he recently got a faculty position at the University of Kansas. Chris Wentland is a PhD student in my group. And David Zhu is also a PhD student. And he is about to graduate and is going to join Facebook's augmented reality team. And all of the work that I'm going to show here is part of a larger team effort that comes under the Air Force Center of Excellence. So this is a center that I direct at the University of Michigan, and we're collaborating with the University of Texas, NYU, and Purdue. All right, now before we start talking about reduced order modeling, let me spend a minute on the broader landscape of modeling. Of course, at the very top, we have the high fidelity models, which are expensive in many problems, but also intractable in others. And then we have two classes of models, and I want to make a quick distinction here because sometimes there is a tendency to mix the two. So we have what are called as reduced fidelity models, which rely on physical simplifications like asymptotic analysis or going from 3D to 2D. And then we have reduced order models, which are a more mathematically formal reduction, which means we're going to be solving the same set of equations as the high fidelity model, but we are going to be solving them on a much lower dimensional manifold. Okay, so this is what I call as reduced order models, and this is going to be the focus of today's talk. Now, as far as reduced order models go, again, there are a very large number of ways in which you can develop reduced order models. I'm specifically covering projection-based reduced order models. Again, so you have a given high fidelity model. In some of the applications I'm going to show, you have 100 million degrees of freedom or 1 billion degrees of freedom. And then the hope is we can find a low dimensional manifold, and that manifold is informed by data. And then we project these governing equations onto that manifold, and you go from solving an equation with n degrees of freedom to something with k degrees of freedom. And in the examples that I show, we basically go from 100 million to order of 100. So the key thing is, how do we extract this low dimensional manifold? It can be done in many different ways. The simplest way is to use a linear reduced basis. So you go from your high dimensional set of unknowns to a lower dimensional set of unknowns, and the transformation is through a linear basis. But again, this can be nonlinear as well. Let me get rid of this. Yeah, this can be nonlinear as well. And then, as I said, we want to solve the same set of equations. So the challenge here is to ensure accuracy when k is much smaller than n, and also be efficient, because there are many ways in which you can project these equations to a low dimensional manifold, but the resulting equations end up costing the same amount of computational effort, because typically high fidelity models are have a sparse structure, and reduced order models have a dense structure. Okay, so it's not just enough to compress it, it's not just enough to project it, but we also need techniques to make this efficient to evaluate. These FR has to be efficient, in other words. All right, so, and this is not a new idea. They've been pursued for at least 2 to 3 decades. But when it comes to mature applications of projection-based ROMs, most of the applications have been restricted to linear or mildly nonlinear problems, or elliptic problems, highly viscous problems, etc. So this is actually a commercial offering from a very successful commercial offering from a company called Axelos. And so they can basically build reduced order models of a very, very complicated structure like a ship. And they can model all the joints and everything. But again, the dominant physics tends to be linear. So it is possible, and it's possible to get a lot of acceleration here. Okay. But the motivation for our work, and this is also the center that I mentioned, comes from a need to develop reduced order models of very, very stiff multi-scale nonlinear transport problems, such as the problem that you would encounter in a rocket combustor. Okay. So shown on the left is one injector in a rocket combustion chamber. So you have oxidizer coming in this small annulus, and then you have, fuel coming in that small annulus, oxidizer coming in the main post here, and then you have these chemical reactions. So running a high fidelity simulation, as we do for one such injector flow field, has about 100 million degrees of freedom and takes about 1 month on a 1,000 processor cluster. Okay. So the problem is a real rocket engine, if you take SpaceX's Merlin engine, for instance, has hundreds of these injectors. Okay. So to do these calculations, it's going to take pretty much a year of runtime on, even if you have a 10,000 process system. So the challenge is not only that it is difficult to simulate these problems and they're highly stiff, it is that it may not even be possible to simulate the full system, but then we're talking about reduced order models for the system, right? So that's what, that is the challenge that we are faced with. And towards the end of this talk, I want to show that, not only do we want to make these kind of ROMs possible, we want to use those reduced order models to explore the effect of, what if I have an engine with 300 injectors arranged in a certain way? How can that change? How does the flow field change when I have an engine with 400 injectors arranged in a certain way, right? So these are basically non-continuously parametric problems, and this is non-parametric in the geometry, etc., right? So these are the kind of problems that we want to tackle. All right, so that motivates reduced order models. Now let's go a little deeper into how these are formulated. So let's say we have what I call as a full order model. So this is basically your high fidelity model equation. So you can think about taking the Navier-Stokes for that rocket, discretizing in space. So you end up with a set of ordinary differential equations of very high dimension. And then, of course, you have to discretize in time the full order model. So you can use a linear multi-step method or whatever your favorite method is. And then the first step, when you go with linear projection-based ROMs, is to take this high dimensional variable and then write it as a decomposition. Okay, so the decomposition is you have a reference state, which is steady, right? So this is the steady part. And then you have a scaling matrix, and then you have your basis matrix, and then you have your k-dimensional set of, let me make sure. Okay, let me make sure I use a pointer, so that highlighter, so you can see it. All right. So you go to a basis matrix, and then you go for a k-dimensional set of unknowns, right? So this is the reduced representation. And then the two very standard ways of deriving the reduced order models. One is the Galloquin projection. So you take this basis and then you use it as the test basis, and you apply it onto this equation, you get this very simple set of equations. So these are equations for k unknowns. And then the other widely used technique of late is the so-called least squares Petrov-Galloquin method, which basically wants to minimize this residual in the reduced dimensional space of coefficients. Okay, so this is called the Lspg method. Now, very quickly, why do we need Galloquin Lspg, and what are the advantages and disadvantages? If you take a simple linear dynamical system, and then like, let's say this is your linear dynamical system, you discretize it, and then you use the decomposition. This derivation is in this paper that I've just cited here. So if the discrete full order model is asymptotically stable, and many times it is, if you have a stable J and say a backward Euler, then the reduced order model based on the Galloquin approach is also asymptotically stable under some conditions. Okay, for symmetric systems, this condition is usually trivially satisfied. So Galloquin methods will remain stable, but for general systems, they may not be. Okay, and then the same setup, when you apply the least squares Petrov-Galloquin ROM, you can show that the least squares Petrov-Galloquin ROM is asymptotically stable with no further assumptions required. Okay, so the addition of the least squares stabilization brings global stability for the linear system, of course. But then the challenge we're facing with is when we apply the state-of-the-art ROM. So when we started the work for the center a little more than 4 years ago, and we started with least squares Petrov-Galloquin and Galloquin ROMs, they were never stable. They were never stable because the kind of physics that is involved in rocket combustors is I must say, pretty nasty, right? So you have interactions between acoustics, flow, and reaction. And unlike gas turbine combustors, in rocket combustors, the pressure perturbations themselves may be extremely high. They may be 10 atmospheres, even the perturbations. And then there is multiscale phenomena involved. And then perhaps most damningly, the stiffness in these equations is incredible. So if you look at this image here on the right, and you look at the values for the heat release, I think it will give you an idea how stiff this is. So basically, the state of the art was not good enough to simulate these kinds of reduced order models. Okay, so today's talk is, can we solve that problem? A, can we solve that efficiently? And also, can we be truly predictive, right? By truly predictive, we have to not just predict things that we've not seen before, but we want to do so on geometries that have not been seen before. Okay, so that's the challenge that we're going to address. So I'm going to touch upon 3 things. The robustness and accuracy, how do we make it work? And then adaptivity, meaning how do we make it predictive for future state? This is always the challenge with data-driven models, right? They're nice in principle, but when push comes to shove, they don't generalize well. So how can we address that? And of course, how can we go after intractable problems using these reduced order models, and how can we enable them? Okay, so that's the plan for today. All right, the 3 things to take home again are related to this. So the high level picture is, yeah, we are going to introduce some new ways of formulating the ROM so that these kind of simulations are possible. And we're going to be using adaptive spaces, right? So earlier I showed you the base is V to be static, but then we make it adaptive. And then the third part, we're going to be building reduced order models for these unit problems or components. And then we're going to stitch each of those ROMs together and integrate them as a network to predict things where, you know, like I said, a full order model is not possible for the whole system. But by developing these component ROMs and integrating them, we can enable this. Okay, so that's the plan for today. All right, the first part, and pretty much everything in this part is covered in this paper, which was just accepted by JCP, the Journal of Computational Physics, and there's also an archive version. So what do we do, right? Again, just like before, we start with the discretized full order model equations. Let's say you want to run backward Euler. And then we introduce pseudo time stepping, right? So what is pseudo time stepping? It's basically a variable transformation. So you go from your variables Q to another set of variables S, okay? And we do this for various reasons. One is to reduce stiffness. The other is to make it better conditioned. And also in combustion problems, switching variables can also help us compute certain quantities that we cannot, okay? So, but basically after this variable transformation, we also introduce a so-called pseudo time stepping, okay? So we add this, we take the same set of equations as before, and then we introduce a pseudo time step, which goes from, within every physical time step, you do a number of pseudo time steps, okay? And the pseudo time step index is P. And then we can get the fully discrete residual after linearization. But the important point is we do not lose any accuracy in the physical system because of the linearization. It's just something to get a set of equations to converge to, okay? And then the key step is we take these discrete equations and then we do the reduced decomposition, okay? So these basis coefficients can be static or adaptive. Just as I said earlier, there's a reference state, a scaling matrix, a basis, and a set of unknowns. Instead of Q, we go to S now. And then we introduce the least squares formulation, just like in Lspg, but on this system, the subiteration system. And then we minimize the residual to find what is the next update in the reduced basis that I need to make. Okay, so this is discretely consistent because every subiteration now is symmetrized. Okay, so if you look at the paper, there are a little more details, but end of the day, what ends up happening after we do all of those steps is you get a different test basis which changes in pseudo time. So this is how the basis looks like at pseudo time level P-1. It has these multiple levels of scaling. And then the actual reduced order model after the projections looks like this, right? So this is, so you want to go from subiteration P-1 to P, and then you have these symmetrized transformations. So after all the steps, as I mentioned, it's very important that we get discrete consistency at the subiteration level so that all the robustness properties and conservation properties are not lost. It's symmetrized and globally stable at the subiteration level. It's conservative. And then if you look at the paper, we have some additional things that we do to improve local stability. And unlike the least squares Petrov-Galloquin method, we can apply this to explicit schemes as well, okay? I'm going to skip this. So again, this is a little more of a nuance. It is that if you want to reduce the cost of this ROM, you need to do some additional steps called hyper reduction. It basically involves some kind of sampling. And again, if you look at this paper, it's very detailed on how we do it and how we implement it at scale. But the bottom line is, after doing all of this, you can get, at least for some problems that we've shown in the paper, we can get a speed up of a factor of 10,000 for very minimal loss of accuracy, okay, for a very, very complex problem. So that's the goal. So now let's see some results. So here is one of the problems that I showed earlier. It's a coarse version of it, so we can do a large number of tests. So it's, again, a model rocket combustor. Oxidizer comes in here, fuel comes in here, reaction happens here. And this has about 5 million degrees of freedom because each computational cell has 10 degrees of freedom. There's some details here about what kind of kinetics model we're using. But the bottom line is we can achieve significant reduction. So again, this is the error with respect to the dimension of the reduced order model. So we can pretty much go close to like a ROM dimension of 20 to get I would say less than 2% error in some of the quantities that we are tracking. And of course, if you go for more higher dimensional ROM, your error decreases. So again, here are comparisons of the flow field. So this is the full order model with 5 million degrees of freedom. This is the reduced order model with 20 modes, 20 degrees of freedom. And here is a reduced order model with 60 modes. And the paper will have more information on how much the cost reduction is. In this case, we can report about order of 1,000 reduction in computational cost. Okay? So these problems are possible. And again, more of a nuance here. So this is, we built the infrastructure in a modular fashion so that it can scale and it can be used by others. Okay, so everything was good, but what are the disadvantages? So why do we need to do more? It is the fact that, of course, we're able to solve problems that were not possible to be solved before. But then if you look at prediction error, it's still reasonable, but in the future state, you know, during the reconstruction phase, this is basically the data that it has seen. It is able to give roughly about 1% error, but then the error increases. It is stable and it is still predictive, but the errors are somewhat higher, right? And when we go to harder problems like the full-scale rocket combustor, this may not work so well, right? So how can we improve this? So that's the second part of the talk. One way to improve this is to go from linear to nonlinear manifolds. We've done the same kind of explorations, but I'm not talking about that. Instead, I'm going to be talking about adaptivity. Okay, sorry, there are so many blocks here, but I do wanted to impress upon you that it's not one or two things that make this kind of an effort or ambition possible. So there are many, many things that we're doing in the center. Everything below this line is what we're working on. So what I spoke about so far is basically this box here, consistent stabilization with transformation. I just mentioned you can go to nonlinear manifolds. What I'm going to do in the second part of this talk is the idea of using adaptive basis. And then the third part of the talk, I'm going to cover the truncated domain training. Okay, so that's again, the high level picture. All right, adaptivity. So what's the idea? So for the ROMs to be truly predictive in problems dominated by convection, transport, multiscale problems, a static basis may require too many modes. Okay, so if you go from linear to nonlinear, that situation may improve, but then nonlinear manifolds have other issues, right? So making them very cheap is hard. Okay, so this is an example from one of my colleagues, Ben Perstorfer. So he basically says if you just have a Gaussian pulse, a sharp Gaussian pulse that is moving from left to right, and you do a POD or a static basis decomposition, you would need to keep a very large number of modes to be accurate. Whereas if we have a basis that changes in time, you can get away with much less number of bases. Okay, so here is the idea. So let's say you have a high dimensional problem. In this case, high is 3, right? So this trajectory is the trajectory of the dynamical system. And if you want to get a reduced dimensional manifold of dimension 1, this is the best you can do, right? So this orange line, this black line is the best you can do. But then if you're able to like adapt the basis locally along the way, then you're going to basically, these small lines are supposed to be tangent to these spirals. But basically at many of these snapshots, we construct adaptive basis on the fly. And of course, for the adaptive basis to be viable, there are some requirements. It has to be a low rank, there has to be some kind of low rank structure in time. And the residuals has to be localized. But the beauty of this approach is you require very, very small amount of offline data because we're actually adapting on the fly. Okay, so the main formulation is in this paper by my colleague, so I will defer to that paper for a lot of the detail, but I'm just going to give you the high-level idea here and then show you the results. Okay. So again, the idea is simple. We are still using a trial basis V and a test basis W, as I mentioned earlier, but these become functions of time, okay, instead of just being static. And I just explained it in the previous slide. And these bases are basically updated using a rank 1 update at every time step. And these updates, alpha and beta, are derived by solving a small optimization problem at frequently. Okay, so you don't do it at every time step, but every n time steps, you're going to be solving this optimization problem, which is nothing but a minimization of the residual. And there are techniques to make this to solve this very fast. And yeah, here is an example, an example that looks simple but incredibly hard to get with projection-based reduced order models. So just a 2D non-reacting mixing layer, you have two streams at different velocities and temperatures mixing. And if you monitor the pressure at some probe location, it is highly chaotic, right? So it's hard to predict because, the future state has not been seen before when the ROMs are predicting. And again, if you use a static basis, even if you use 200 modes, you can't capture all of the relevant things in the training data, and it fails catastrophically when you do future state prediction. But then, again, this is the full order model. This is the 20 mode reduced order model, but with the adaptive basis. And at least to the naked eye, you can't make out much difference. And, the same thing here. So here we basically train the reduced order model only for this instant. Okay, so this red spot, 0.167 milliseconds, is the training data. Okay, so the rest is pure prediction, and it does very well. Whereas if you look at the static basis reduced order model, even if you go to 60 modes with more data, or even with 120 modes with a lot more data, you're still struggling. Okay, so that's again, tells us that adaptivity works. But again, there are still some challenges in making it as efficient as the static basis reduced order models, but we're working on it. And then we can also, now we're doing true prediction. Okay, so what if we just train the adaptive basis ROM offline using that data on a different problem, and then suddenly I change the velocity of this stream to some number that was not in the training. So the adaptive basis still captures it, whereas the static basis really struggles, and it's trying to solve a different problem. Okay, so that's a step towards true predictivity. Some more results here, which I will skip in the interest of time, but again, driving home the point that for much more complex problems than what I just showed, the adaptive basis can really has the potential to be truly predictive. Again, a lot more results, but the point I want to make is, yes, we can make true predictions, but it is not as if we're obtaining a speed up of 10,000 or 100,000 that I showed earlier. The speed ups that we're able to achieve currently are mild. It's order of 10 maybe, but then we're working on techniques to make it even faster. And many of the results that I showed, at least at least for the simpler problems, you can find in this website where we're trying to organize a workshop where we want the community also to work on these kinds of problems. And there is some code for 1D problems that Chris has put there. All right, so now the third topic, which is tractability. And again, let me remind you what the tractability challenge is. I told you that simulating the flow field of one injector takes about a month on 1,000 processors, whereas the full-scale engine takes a year on 10,000 processors. Okay, so it's not possible to have the full order model. So can we still construct a reduced order model of a full-scale engine? So this is not a standard parametric ROM problem, right? So we want to be able to use these ROMs to solve a class of problems, a class of systems. Of course, we can't do a ROM for everything. It has to be some class of system. And we want to use that ROM to study how a rocket engine with different number of injectors arranged differently. We want to analyze engines that have different combustion chamber shapes and sizes that change in a non-parametric fashion. And we also want to study an engine with different fuel and mass flow rates. This is more standard. This is more a parametric ROM problem, but there are many other things that we want to do. Okay. So what is the approach that we take? We take a unit, which is one injector, as I said. We are able to do a full order model of an injector. It's still expensive, but it's possible. Okay. So we're going to take the full order model, and then we're going to give it all kinds of artificial forcing, right, to simulate the kind of things that it is expected to see when it is deployed in the full scale setting. So we may want to force the full order model in transverse direction to excite the span-wise dynamics that you will see will happen in the full scale system. We also want to give characteristic perturbations so that the downstream responses are simulated. And we also want to ensure that there is enough small scale content. Okay. So we basically develop these full order models for these unit component models, so component problems, and then we develop reduced order models of those components. And then we, as I mentioned in the beginning of the talk, we stitch together these reduced order models and integrate them so that we can do a full scale engine, right? So of course, the highly geometry dependent parts that I've shown here, we can use a full order model because the physics here is mostly acoustics, right? And acoustics, even though the perturbations are high, you don't require extremely fine discretizations. Here is where you have that incredible amount of heating and stiffness and reactions and all of those, whereas here you just have mostly acoustics. But then like I said, we want to do different kinds of arrangements of the ROM to do the engine with different injectors. And of course, we can also do combustion chamber shapes that we can analyze. Okay, so that's the goal. And here is how the approach works. Again, before doing this big problem, we want to do this in a smaller scale problem. So we basically took a quasi 1D rocket combustor. And of course, you don't have all those reactions in quasi 1D. So we basically added some type of a heat release that is oscillating. And again, so what do we want to do? So let's say the challenge in this problem is I want to train a reduced order model for a small domain. And I want to use the reduced order model to analyze how the system behaves when the combustion chamber length is increased or decreased, okay? And you can immediately see what is happening. When the combustor length is large, in this specific case, there is a lot of amplification, okay? So the system goes unstable. Whereas when the combustor length is short, any perturbations we give to the system, they basically damp out, okay? So there is still a small amount of oscillation, but much less than what we saw earlier, okay? So this is an example of an unstable system, and this is an example of a stable system. But and these are geometrically different, right? So we want to develop a ROM of a small part, and we want to use the same ROM with the geometrically changing parts. So this is how the approach works, as I said. So we take this part, which is common to all the engines that we want to simulate. We run a ROM with various types of perturbations, and then we run the full order model with various perturbations of this truncated domain. And then we train a portable ROM, and then we stitch together this ROM with this full order model, okay? So again, the reactions are happening here, and here it's just acoustics. Okay, so that's, and then we can stitch together this ROM with different combustion chamber sizes, and we still want to be able to replicate that behavior. And all of this is in this paper. I can give you the full reference, but if you look for Zoo AAA Journal 2019, you'll see this. Okay. Okay, and again, if you look at the results in the paper, you'll see that the reduced order model is able to do a really nice job predicting the unstable behavior in the long chamber, the stable behavior in the shorter chamber. And it is also able to do predictions in unseen combustion. I mean, actually, both of these are unseen, but the kind of perturbation frequencies we introduced in the truncated domain training, it was able to, the multi-fidelity model was able to make great predictions even outside of the frequencies. So that's, and the reason why this is possible is because we're still solving the equation, so there is still some physics to save us. All right, so now how do we do for the full rocket combustor? Same thing, let's say I have a rocket combustor with 5 injectors. Can I just build ROMs for some of these units and then put them together and use them for prediction? So here is first the sanity check. The sanity check here is we broke this down into 5 individual injectors. We trained them, and then we put all of those trained 5 injectors together, and we can recreate this. So it almost looks like an innocuous exercise, but it took us 4 years and many millions of dollars to get here. But then the challenge is, and we can do that very well. Okay, when we build 5 individual ROMs and stitch them together, we can basically nail it. So that's a accomplishment, but it doesn't help anyone, as it does not help the Air Force engineers, for instance. And we can also do future state prediction, which is nice. But then the real challenge is, you know, we want to do this problem with hundreds of injectors, and you want to train just a few. Okay, so this is how the strategy would look like. Clearly, the injectors in the middle of the combustion, in the middle of the injection plane, would see different physics from injectors that are right on the walls. Okay, so there has to be at least 2 types of unit domains that we have to consider, right? So one is the interior ROM, and the other one is the wall element ROM. Okay, so we still haven't solved, you know, Elon Musk's problems, but what we're doing currently is, again, as I said, assume that this is the injector we want to simulate. First, we create a training for the interior domain, interior component, and with perturbations, of course, because there is span-wise dynamics in the real system. And then we train a reduced order model just for the injector on the wall, and that is also like done with forcing. And so we basically now stitch them together, right? So we just trained 2 components, right? An injector ROM and a wall ROM. So then we put 3 of those injector ROMs in the middle, and then we put this this reduced order model on the left that we trained, and then we mirror it. Okay, when I say we are mirroring the reduced order model, we just basically transposing the bases to reflect the coordinate system. But this is still a chaotic problem, right? So the mirroring does not mean that you're seeing everything that you're supposed to see. But this general approach is scalable to a large number of injectors in the 2D setting, right? In the 3D, you have other things to worry about, but again, it's a start. And again, long story short, such networks with adaptive bases, it is possible to be predictive. Okay, so this is the full order model. And then here is the ROM network trained using just 2 component ROMs, and then replicated, stitched together, and then deployed to do the prediction. So here is the black is the pressure at one probe location from the full order model. The gray is the ROM network. And then this is the power spectral density of pressure. So the ROM is not perfect, obviously, because there is a lot that is happening, but it's picking up all of these, all the essential features that we care about. Again, I don't want to give the impression that this problem is solved, because the training, the networking, everything works well, the adaptive basis works well, but adaptive sampling is required to speed up the adaptive basis. So that's something that we're actively working on, right? So it's not a solved problem in terms of efficiency, but in terms of being able to do future state predictions and being able to replicate behavior for a model with unknown full order model, we can still we can do this. All right, so let me summarize here. So what problems are we? Why are we doing this work? First of all, right? We want to, so the extreme stiffness, nonlinearity, and multiscale nature of the problems that we're going after poses robustness and efficiency challenges. And existing static and linear manifolds are ill-equipped for predictivity. And we want to do ROMs of systems for which you cannot afford even a single simulation of the full order model. So what are we doing? To address all these robustness issues, I introduced to you an approach that we call as model form preserving least squares with variable transformation. I just said everything that is in the method. And then to overcome the deficiencies of static or linear manifolds, even nonlinear manifolds have similar issues. We go to adaptive basis, and it basically overcomes the Kolmogorov n-width barrier. And we're able to do true parametric predictions. Again, not a done deal, because we still have ways to go to make this more efficient. And then to enable ROMs for systems for which you do not have full order models, we use truncated domain training and then stitch it together. So what are we working on? As I said, adaptive sampling to make the adaptive basis more efficient is one. And then we're also exploring non-intrusive and semi-intrusive formulations, so you can find more publications in our center. But again, I spoke about these three things, but there are many other things that are happening. You can look at it in our center webpage, and we thank our program managers and the Air Force for funding this work. All right, so I will stop here, and I think I'm right on time. 11:45 or 4:45, and I can take questions now. Thank you.
Okay, well, thank you, Karthik, for the great talk. And if the audience has any questions, please do feel free to drop in your question in the QA panel, which should be at the bottom of the Zoom app, at least in my computer. So there is already a question actually from George Draculas, and another question from George Papadakis. I will start from George Draculas. So do you believe that reduced order modeling based on non-intrusive deep learning methods are also a state-of-the-art methodology? They are able to efficiently reduce the dimensionality, predicting time, and account for the uncertainty quantification of the boundary conditions.
Yeah, so that's a very good question. If you had asked me that question even 2 years ago, I would have said no. I mean, that, you know, that you just need too much data to solve these kinds of problems with truly non-intrusive methods. But our own research over the past couple of years, and that's why I have this box that says non-intrusive, they're actually giving these intrusive ROMs a run for their money. I mean, earlier I always used to think, okay, these non-intrusive methods are expressive, but then you probably need too much data to train these and be generalizable. But I can point you to a few of our papers where just even in the projection setting, using a neural network to advance the system forward in time. And there are some new approaches. If you look at one of our recent papers, it was accepted to NeurIPS. On conditional parameterization, we are actually being able to predict mesh-free solutions by taking data at not only from the temporal snapshots, but also in space. So again, as I said, 2 years ago, I would have certainly said no, but currently I say, yes, they're very promising. And they might even beat these intrusive ROMs. On the other hand, the adaptive basis approach, for instance, that we use, which is very successful, as you've seen, the adaptivity is based on computing a residual, right? So we know the physics, so we basically are able to compute a residual and guide the adaptation. In a non-intrusive ROM, you don't have the equation in hand, so adaptivity becomes very hard, at least the way we think about it. So pros and cons. Currently, I would say the gap between intrusive and non-intrusive is small, but it's closing. But intrusive is ahead. But yeah, there may be some new things that come about. In terms of accounting for uncertainty, quantification of boundary conditions, I think that goes into adaptivity, right? So non-intrusive and deep learning methods are amazing at recreating what they've seen before, right? Or what they can understand. But if something changes, obviously the flow topology changes to something that has not been seen before, there is no way that non-intrusive ROMs can get it. There is no way intrusive ROMs can get it, but adaptivity helps there. So yeah, the gap is narrow, but currently I would put a little more trust in intrusive ROMs, but that can change if I give the same talk 2 years from now. So I don't know. We'll see. All right, second question.
Thank you. Yeah, a lot of things can change indeed in a couple of years. And George Papadakis, he's asking a question on chaotic systems, which actually had myself as well. So regarding the predictability of chaotic systems, of course, this depends on the size of the unstable Lyapunov exponents of the system. So how many, and also, how big is the unstable tangent space. Yeah. So a reduced order model will introduce small deviations with respect to the full order model. So is it realistic to expect that the reduced order model will follow the real system for a long time? And isn't this limited by the very nature of chaotic systems, which are unstable, linearly unstable?
Yeah, 100% agree that, it is certainly limited by the physics of the chaotic system. And I want to basically say a ROM will introduce small deviations. So it is certainly not realistic to expect the ROM to follow the real system for a long period of time. 100% in agreement if you have a static basis, okay? But with the adaptive basis, because we have the full equations, right, at our disposal, it is possible to get these small deviations to be very small. So maybe if this is a really chaotic system as I showed you, right? So we are just using the training in this region, and then we are letting it fly. And of course, you do see some small deviations. Maybe if we really march it for much longer time, you will certainly see some deviations. But the hope is we're not after every single deviation that happens in the flow, right? We want to make sure that higher order quantities of interest are captured well. So in that sense, adaptive basis can certainly get us there. But if we are going to replicate all the chaotic trajectories, whether we have a static or adaptive or nonlinear basis, whatever it is, there is no hope. But the hope is, we're after things like this. We want to make sure we capture this behavior, like this linear growth, nonlinear saturation. We want to make sure that we capture the important features, like, sorry, I'm skipping through here. We want to basically capture the important things, but yeah, we'll never be able to follow all the trajectories. And I don't think that answer is going to change in 2 years or 15 years, but we can get quantities of interest modeled well. But yeah, good question, and certainly a comment I agree with.
Yeah, and I follow up on that as well. So did you have the chance maybe to compare, instead of the time accurate or the time instantaneously, the time instantaneous solution, did you compare maybe the statistics of the solutions, like even first order moment or second order, with respect to the full order model? Because that could be a more robust way in a chaotic system to, compare as a metric of interest.
Yeah, I think I didn't talk about it much, but when I showed some of these results earlier, they were basically like L2 norm of the error in the entire flow field and things like that. But yeah, again, there's many complicated things that happen in a rocket combustor. So, sometimes if the wave that comes back is too strong, it can actually shut off the reaction, right? The engine can go cold. Whether we're able to capture all those kinds of features, I don't know. But yeah, we've tracked like moments and spatially averaged quantities and things like that. And again, I don't want to claim that we can solve all of this really well for these kind of complex problems yet, but yeah, we are making progress.
Excellent. Is there any other question from the audience? Please do drop your question if you have any in the QA panel. Otherwise, I will continue because I have a few questions actually, but I wanted to give some space, of course, to our audience here. Well, one question I had is about the adaptivity and the adaptive basis. Did you inspect? I mean, you showed basically the reduced order model in action, comparing the flow field with respect to the full order model. But did you inspect also what each mode, I mean the dominant modes at least, are in telling us physically? Is there a physical structure, and how does it change with respect to the static basis?
Yeah, so what the adaptive basis does is, so, if we have like problems that are dominated by a few modes, right? So more or less the mode structure won't change. But think about, sorry, I want to, this is, how do I turn off the highlighter?
In PowerPoint?
Yeah.
Oh, I don't use PowerPoint. Sorry.
Yeah, so again, it's very hard for me to go back now. And even the escape is not working. But
escape, maybe you can stop sharing the
screen. Yeah, even that is not. Okay, I think I was able to do that. Okay, so let me start sharing again. Sorry. Yeah, so I would like to give a nice physically sounding answer to that, but end of the day, it's just too much dependent on the topology, right? So for instance, let's take this one, right? So this is just a Gaussian pulse, right? That's moving to the right. If you do a POD, you're going to see a lot of these waves, a lot of these modes that show up. And the perfect adaptive basis would just be one basis that just follows the pulse, right? So and this is a pulse, this is a linear advection, so there is nothing changing, right? So the adaptive basis would just replicate the entire flow field with just one basis. And the basis is actually the flow field at that time step, right? So that's why it becomes hard, because these problems are dominated by convection, and there are also a lot of these coherent structures that move around. So if we just had like one or two things that are driving the flow, I think we can get a lot more physical interpretation out of these adaptive basis modes. But in reality, especially for these kinds of problems, it is just fitting, right? It's basically finding what is the best fit that I need to do to represent this particular snapshot. And after a while, that will change. So the short answer to your question is it's more, it's less physical and more, I I think, fitting the image type of thing.
Okay, okay, that's good. And let me see, there is a question. Oh no, there is a comment from Andrew. So I don't see other questions. I have maybe a final quick question. So
yeah.
If I understand correctly, also you mentioned that, I mean, the reduced order models you want to devise are for eventually, or even now, for real-time sort of, predictions, right?
No, not real time. I mean, not in this work. Okay,
but
so
I think it was mentioned at some point it was real time. Maybe I got hijacked there for.
No. So
because one question was what is the computational cost basically of solving the optimization problem for the adaptive basis? That was my question for real time prediction.
Yeah, so let me answer the second question first, and then the first question, right? So yeah, these are expensive problems, and we are actually going after ROMs of the full flow field, which means we can reduce this by a factor of 1,000, which is still far from real time, right? But if you're going, I must not have said real time in this talk, but we do real-time work in my company, Geminis.ai, and few other projects. There, we don't go after the full flow field, we go after quantities of interest, right? There we're going after a few quantities, and that can be done in real time. But your question regarding the real time was?
But my question was
for the adaptivity itself.
Exactly.
The adaptive basis is expensive. And for maybe we've not achieved it in problems of this complexity, but for something like Euler, we're able to show that you can actually get good acceleration with adaptive basis as well. So I just spoke, there are two parts to the adaptive basis. I just spoke about one, which is how to find the basis. And then there is also adaptive sampling, which is how do you solve that optimization problem with just a few samples. And Ben Perstorfer's paper talks about how to choose those samples adaptively also. So by adaptive sampling, you can reduce the cost of the adaptive basis. And we've not reduced the cost of problems of this magnitude yet with adaptive sampling. There are still some issues to work out, but for simpler but still complex problems, we're able to get the adaptive sampling to give us low cost. But yeah, it is if you don't do adaptive sampling, the adaptive basis is going to be as expensive as the full order model.
Yeah.
Okay, because you're effectively carrying the full order model at every time step.
Yeah, exactly. Yeah.
But the sampling.
That's my question. Exactly.
Yeah.
Excellent. All right. So unless there are other questions, I don't see any other question. I think, we are at the end of our hour. So, well, let me thank you, Karthik, Professor Duraisamy, for your great talk. I'm sure I will follow up personally offline, if I may. And thank you for taking time, of course, and accepting our invitation. And I hope to see you sometime in person. So thank you very much again.
Yeah, looking forward to that as well.
Yes.
Thank you.